guys, so this video is going to cover shapes of molecules. So if you are watching this because you missed your lesson, it probably will be very helpful if you first go to Moodle and copy up the notes from pages 11 through to 13. So this is page 11, 12 and 13. It probably won't mean much to you at the moment, but it will be useful when I'm talking about the shapes of these molecules. So if you go and copy up those pages first, that will be very useful. Obviously, if you're watching this video as part of revision, just get your structure and bonding notes open to this page, so it should be already done for you. Right then, so when you look at those notes pages from 11 to 13, you will probably drawn out examples of different molecules. Now, normally when we draw out molecules, especially at GCSE, we would do this in a 2D kind of way. So I'm going to use methane as an example, so CH4. So when you did this at GCSE, or actually since you've come to college actually, you may have drawn methane like this. Now that isn't wrong, all it is just that it's the 2D shape. Now when you look at your notes, there is an example of methane and you might have seen that this was drawn slightly different. So we still had the carbon in the middle, we still had one hydrogen like that, we had one like that, and we had one like that. So the 2D shape wasn't wrong, it's just that the shape is now being drawn as a 3D structure. Because obviously molecules are kind of moving around and they aren't all flat, they do have a 3D shape. So when it comes to actually drawing molecules in this section, we have to represent them in that 3D shape. Okay. So we've got the carbon in the centre and it's still bonded to 4 hydrogens, exactly like we did in the 2D. Now you will notice these 2 hydrogens have the same bold sticks that we did in the 2D drawing. Now these represent the hydrogens that would, when you actually have this shape in front of you, would fit flat to the page. So the bold straight lines represent covalent bonds that are basically in line with the board or the piece of paper you have in front of you. Now this little wedge here is also a covalent bond, but it's representing a bond that is kind of coming out of the page towards you. So you kind of have to imagine that that bond is coming outwards towards you. And then finally, we have this little dashed line, this little dotted line. Again, this is still a covalent bond, but this is representing a bond that is going backwards into the paper. So this is just kind of a way of representing molecules in a 3D kind of shape. So when you're asked to represent molecules as a 3D structure, you do need to take into account that some of the bonds may be coming out of the page, some might be going back in, so we need to kind of represent them as such. Right, so the main thing we need to kind of consider now is, why do molecules have certain shapes? Okay, why am I drawing these different molecules with these certain shapes? Well, the shape of a molecule is determined by a few different things. So it's electron pairs around the central atom, so that's just basically how many electrons the atom in the middle has around it. It also is determined by the number of bonding pairs of electrons. and the number of lone pairs of electrons. Okay, so these few things. So when you identify what shape a molecule has, you will have looked into the number of bonding pairs and the number of lone pairs of electrons around that central atom. I'm going to show you a way of working that out, but before that I'm just going to talk a bit about the electron pair repulsion theory. Okay, so this basically is exactly what it says on the tin. It's this idea that electrons repel each other. Well, of course they do. Electrons are all negative, so these negative particles don't want to be near each other. So we will always have pairs of electrons. In a covalent bond, there is a pair of shared pair of electrons, and a lone pair is a pair of electrons. So when we're talking about this, we're always talking about pairs repelling each other. So let's look at the first example you wrote down in that table, so BeCl2. So this is quite a kind of simple one. So your beryllium is in the middle, and it is bonded to two chlorine atoms, like so. So beryllium just has two bonding pairs of electrons. So we've got a pair of electrons there and a pair of electrons there. Due to the number of electrons beryllium has, it doesn't have any lone pairs, okay? Again, I'll show you how we work that out a bit later on, but first we'll just discuss why things have this shape. So, basically, beryllium has a pair of electrons in this covalent bond and a pair of electrons in this covalent bond. So these electrons want to repel each other, and they want to be as far away from each other as they possibly can be. So in order for these two pairs of electrons to be as far away as possible, this is the shape that is created. So this is this linear shape, and the bonds are 180 degrees from each other. Okay, so basically all these shapes that you have copied down to your table, they're all because that's as far away as those pair of electrons can be apart from each other. So moving apart from each other. Right, what you do need to know though is, like I said, it all depends on bonding pairs of electrons and lone pairs of electrons. Now, if it's a bonding pair of electrons, they will repel each other equally. But lone pairs actually have a greater strength of repulsion. So they actually repel further. So what happens is when you get a compound that has a lone pair of electrons, the lone pair will give a greater repulsion. So I will show you another example. So let's have a look at another example of this. So we've got SnCl2 this time. So you would think, oh well, SnCl2 surely has the same shape as BeCl2, but it actually doesn't. Now, with SnCl2, we now have the tin in the centre, and it does have two bonds to two chlorine atoms. But SnCl2 also has a lone pair of electrons on the tin. So we do have a greater repulsion from the lone pair. So rather than this linear structure that we saw, we now actually have, move tin over, we now have structure that looks like that. Just change my lone pairs to look across this so they can be easily seen. So we now have a structure that looks like that, okay? So rather than that linear structure, we still have the bonding pairs of electrons trying to be as far away from each other, but because of that lone pair repelling a little bit more, we've also pushed our bonding electrons a little bit closer. So rather than seeing that linear structure that we saw in BeCl2, we now have this V-shaped structure with SnCl2 because of that lone pair. So basically, the reason why certain molecules have certain shapes all depends on how many bonding pairs of electrons they've got and how many lone pairs of electrons, because pretty much everything is trying to fit around that central metal ion, and it's trying to fit so basically that everything is as far away from each other as it possibly can be, and this is why we get these 3D structures. So in terms of repulsion, bonding pairs of electrons repel the least, so bonding pair to bonding pair electrons repel the least. Bonding pairs against lone pairs have a greater repulsion, and then if you've got two lone pairs next to each other, they have even greater repulsion from each other. So basically, these shapes that you have in that table are all down to lone pairs and bonding pairs within the molecule. So it's pretty much a case that with this table, you just have to learn this piece of information. You have to learn that if there are two bonding pairs, they will repel each other as much as they possibly can, and they create a linear shape, and the bonds are separated by 180 degrees. For example, BF3, which has 3 bond pairs, for the 3 bonding pairs to be as far away from each other as they possibly can, they create this trigonal planar shape. And this trigonal planar shape, the bonds are separated by a 120 degree angle. So every single one of these shapes is based on their bond pairs and their lone pairs. I'm just going to skip this one, just pop to here. And then on page 13 of your notes, you have the shapes when you have bond pairs and lone pairs. Okay, so if we look at this SnCl2, this V-shaped, we've got 2 bond pairs and 1 lone pair. Now that's very similar to the trigonal planar shape, but the trigonal planar shape has 3 bonding pairs, okay? When you have 3 bonding pairs, you have a 120 degree angle between the bonds. When we include the lone pair now, we only have 117.5. Right, that's because the lone pair here has a greater repulsion. So what that's doing is pushing those bonding pairs of electrons closer together. And this is what it means in the notes by each lone pair reduces the bond angle by 2.5. Because if all those 3 pairs of electrons were bonding pairs, then we'd have that trigonal planar shape as seen in the previous part of the table. But because one of those pairs of electrons is a lone pair, that angle between the bonds is decreased by 2.5. Another example of that is this pyramidal shape, okay? So this pyramidal shape, 3 bond pairs, 1, 2, 3, and 1 lone pair. Now, that shape is similar, not the same, similar to the tetrahedral shape. So here, we've got 4 pairs of electrons, but all 4 of these pairs of electrons are bonding pairs. So they are equally spaced out, creating this tetrahedral shape and giving 109.5 degrees between the bond angles. Whereas when we do this one here, yes, there are 4 pairs of electrons, 3 are bonding pairs, and 1's a lone pair. So because of that lone pair, those bonds are pushed closer together because there's a greater repulsion from the lone pair. So rather than 109.5, we take away 2.5 and we go down to 107. So there's some kind of examples of that. The other bit I wanted to talk about is just a couple of examples of double bonds. So these rarely come up on AQA, but you basically treat a double bond or even a triple bond in the same way as you do a single bond. But rather than bonding pairs, because obviously there's more than 2 electrons in there, we just call them bond areas, okay? So here we have a nice kind of like linear shape because we've got 2 double bonds. They repel each other as much as they can and create the linear shape like before. Here we've got SO3, which has 3 double bonds. We treat them as just regular 3 bonding pairs of electrons, so we get that trigonal linear shape. So you'll see some kind of crossover between the double bonds and the single bonds. Okay, so you've probably been kind of wanting to know for a while, well, how do I work out how many bond pairs or lone pairs there is? So this is kind of our next step then. Right, so how do we work this out? So I'm going to go back to methane again as my example. So the first thing I'm going to do is take that central atom, which in this case is carbon, usually the one on its own, okay, that one on its own. So carbon is my central atom. Right, now I'm going to work out how many electrons are around carbon, just carbon atom on its own. So I'm going to go to my periodic table and I'm going to go to group 4 because that's where carbon is. Okay, so carbon is in group 4. That tells me that carbon has 4 electrons around it, just carbon on its own. Right, now I'm going to look at the hydrogen. So we're just looking at how many electrons are going to be around carbon because of hydrogen. So because there's 4 hydrogens bonded, that means that each hydrogen is using an electron. So because there's 4 of them, there's going to be 4 electrons from the hydrogens. Okay, so because they're bonded 1 from each, we get 4 electrons from the hydrogen. Right, well, what does that mean? Well, that means that around the carbon there's going to be 8 electrons in total. 4 from carbon and then 1 each from the hydrogens. Okay, so that's 8 electrons. Right, so I've worked out there's 8 electrons in total. Now I'm going to work out the pairs. Well, there's 4 pairs. Because if there's 8 in total, if each of them pair up, we're going to end up with 4 pairs. Right, let's have a look at the molecule again. How many of those pairs are bonding pairs? Well, all of them are bonding pairs. Because there's 4 hydrogens bonded to the carbon, all the pairs of electrons are bonding pairs. So in this case, we've got 4 bond pairs and 0 lone pairs. So the BP is for the bond pairs, the 0 is for the lone pairs. So what I would do, in this early stage anyway, I would then go, right, so CH4 has 4 bond pairs, 0 lone pairs. I'd go back to my table and I'd work out that, let's go back to the table, 4 bond pairs, 0 lone pairs. That must mean it is tetrahedral. Right, another example, PCl5. So again, this is in our notes. So phosphorus on its own, phosphorus is going to be my central atom. Okay, I'm going to go to the periodic table, find phosphorus. It is in group 5. So that tells me that phosphorus has 5 electrons in its outer shell. Right, so there are 5 chlorine atoms bonded to phosphorus. Okay, so that means that each chlorine atom, because it's bonded to phosphorus, is going to basically bond with 1 electron. So the chlorines, there's 5 of them, each of them is giving 1 electron to the bond. So that means there are 5 electrons in total from the chlorines, 1 from each chlorine. We don't include any of the other electrons, we only include the electron that is being used in the bond. Okay. Right, so what's that in total? That's 10 electrons in total. So how many pairs is that? Divided by 2. So that's 5 pairs in total. We've got 5 chlorines bonded to the phosphorus, so all those 5 pairs are bonding pairs, 0 lone pairs. Again, I will be like, at this stage, I probably need to still look that up. Obviously, when it comes to the exam, these are the shapes that you kind of need to remember. So all I would do is go back to my table, 5 bond pairs, 0 lone pairs. I've got a trigonal bipyramid, and I would draw it like I would over there. Okay, so last example then. So this time we're going to have NH3, so ammonia. Right, so again, our central atom will be nitrogen in this case. Nitrogen's kind of on its own there. And nitrogen, like phosphorus before, is in group 5. So nitrogen will already have 5 electrons around it. Okay, we have 3 hydrogens bonded, so to the bond, each hydrogen is going to give 1 electron. So we've got 3 of them in total. So in total we'll have 3 electrons from the hydrogens, 1 from each hydrogen. Okay, so this time we have 8 electrons in total. Right, so that must mean that if we've got 8 electrons in total, we have 4 pairs. Now this is when we have a look at the ammonia, because the nitrogen has only got 3 hydrogens around it. So that means that there is only 3 bonding pairs, okay? 1 for each nitrogen-hydrogen bond. So there's only 3 bonding pairs. But there's 4 pairs in total. We've just worked it out. We've worked out that there's 4 pairs in total. So if 3 of them are bonding pairs, that must mean that one of those pairs must be a lone pair. So this kind of helps us work out how many bonding pairs, how many lone pairs there are. So if I go back to my table, if I look up 3 bonding pairs and 1 lone pair, I have a bipyramidal shape, 107 degree angle, and I would draw my ammonia like so. So what you need to take from this video basically is these shapes arise because pairs of electrons like to repel each other, and bonds are a pair of electrons, lone pairs are a pair of electrons. The bond pairs repel the least, the lone pairs repel the most. Okay, and the shapes of these molecules are determined basically by how many bonding pairs and how many lone pairs there are. Right, so what you need to realise now is that you need to remember these shapes from your table. So a great way of kind of quizzing yourself is having flashcards with the number of lone pairs, bond pairs on one side and the shape on the other. And you have to be able to kind of draw the shapes and identify the bond angle. So this part of it is a bit of a recall kind of process. To work out the bond pairs and lone pairs, we just need to do what I just did in the last exercise. So with these shapes, it's all about working out the bond pairs and lone pairs, and then identifying the shape from that. Okay. Right, thanks for listening then, guys.